And in the 80-20 trade-off, these two can get you a lot of the way. But the problem is that in the end, you will still have this annoying 20 or 10 or 5% of data that are locked inside the free text. And if you want them, you need to dive into this messy pile of free text and get them out. Let's take a quick peek at this mess we're talking about. So there are actually a big variety of medical texts. There are forum and social media messages where people like very much to discuss their medical conditions of them and their spouses and friends. There's actually a lot of medical data available publicly. You can see the example here of clinical trials requirements. And there's also Wikipedia and news. You have academic medical papers. And the most important part that we're going to talk about here is the clinical notes and reports. These are the reports the doctor writes while taking care of a specific patient. And they're usually doing it with a big lack of time. So what we get here is a text that on one hand is very professional, but on the other hand is sometimes non-grammatical and hard to understand. Why is NLP healthcare so hard? The first thing you want to do as a data scientist when you get a new problem, you want to take a few lines of code from the internet, let's say sentiment analysis of hotel reviews, do some tweaks to it, and let's go. Would it work? So sadly, no. The healthcare NLP, first of all, has its own vocabulary, syntax, and semantics. Let's look at the two sentences here that are taken from radiology reports. The first one, you just don't understand the word, and it's okay, it's a vocabulary difference. The second one is actually more interesting. Let's examine it. It's a very typical radiology sentence. Midline shift, there's a finding of midline shift, at the level of the septum pellucidum, the location of the finding, and measures approximately 1.5 millimeters the size of the finding. So now you all look at it, and it looks like a pretty grammatical normal sentence, right? So here I got a few of state-of-the-art NLP solutions that actually have hard time to deal with it. And it's because underneath the surface, what happens in the sentence, that there are two compound nouns not used in regular language, midline shift and septum pellucidum, and the word measures, which is used here as a verb, is usually used as a noun. So what happened is that, for example, Google Cloud found here an entity called septum pellucidum measures, which is not an existing entity. Watson did the same mistake. Spacey actually understood that measures is a verb here, but he split the sentences between septum and pellucidum. So we got midline shift at the level of the septum, and pellucidum measures are something, something. So as we can see here, existing solutions don't do good work on this text, and it's not because they're not good, they just weren't trained on this data. Another problem we have is that medical data usually integrates prior medical knowledge and the history of the patient. I'll give you an example from my domain, radiology reports. The work of radiologist is to look at a radiology image, and he creates a report that describes what is in this image. So we would think that the report is just the image in words, right? Wrong. What actually happens is that the radiologist understands what are the symptoms of the patient. He has medical knowledge that might explain these symptoms, and he looks at the image not as a person looking at an image in a museum, but as a detective looking at a crime scene. He's trying to find clues for these specific symptoms, having his medical knowledge. And this is something, of course, that doesn't appear in the free text in the report. And it's a problem when we come to analyze the report. And the last problem we have in our domain is a very small amount of label training data, because A, it's mostly confidential, and B, it's very expensive to annotate. Okay, you can't let mechanical Turkers do it. You need actual doctors or medical students. Okay, so these were the problems. Now let's start talking about the solutions. If you take one slide from this lecture, please take this slide. These are the good news, and I'm going to elaborate on each of them now. There are parsing solutions trained for medical text. We're going to talk what they can give you and what is still left to you to do by yourself. There are a lot of clinical ontologies, and I'll show here how we can use them to inject knowledge into our neural networks. And knowing your data, understanding its specific pattern and specialities can help you very much and create shortcuts. And I'll show 2 case studies, one from Zebra Medical where I work, that will show you how it can be done. So let's start with the parsing solutions. So when I said before that the existing solutions are just not trained on medical text, you probably said to yourself, well, let's train them on medical text. And this is exactly what happened. Who here uses Spacey? Not as much as I assumed, okay. So Spacey is a very commonly known and used tool to do NLP on text. And just a few months ago, Alan and I, about which you heard a few minutes ago, developed a model of Spacey that is trained on medical text. There are also some other open resources, and there are paid resources. And what they all can give you is a correct dependency parsing of medical sentences, which we showed before is hard. They can extract medical entities. The regular solutions extract entities like person, organization. These solutions extract entities like disease, chemical, cancer. And the paid solution can also do some nice stuff. Whoops, sorry. Okay, you can see here, they can do negation. They can tell you that this symptom here is actually negated. And they can do relation extraction. They can tell you that 50 milligrams relation to the medicine Vyonez is dosage. Okay, so this looks very, very good, but we need to remember that it only takes us part of a way. If what our application wants to do is match clinical trials to patients or create a dialogue system, well, it's not enough just recognizing all the entities in the text. And the more big problem is that even if you want only to recognize findings in your text, that's all you want. What sometimes people don't understand is that medical text by itself contains a lot of different languages. Pathology reports would use different terms and syntax than radiology reports. They both will be different from discharge notes and so on. So we saw before how Amazon Comprehend Medical did so beautifully on a discharge report. But let's take a look at the sentence that we showed before, the radiology sentence. It found septum pellucidum to be an organ, which is great, right? We didn't see it before. But it still doesn't understand that midline shift is an entity. And this is because midline shift is a very radiology-specific term. What it actually did do, which is nice, it understood that midline is a direction. It's not correct here, but it's actually a very clinical observation. So as we saw, parsing solutions, good, but can't take you all the way. Let's talk about the second piece of good news. Clinical ontologies. There are a lot of clinical ontologies in medicine, and they were handmade by doctors, and these are great news. What do they look like? So usually they will look something like this. A lot of medical concept organized in a tree structure, going from more specific to, going from more general to more specific. And this screenshot I'm showing here is from UMLS, which is a database containing about 50 different ontologies like this. Another way we can go is we can use knowledge graphs that are taken from DBpedia. They would have entities connected between them by relations. And as you can see here, from here we can learn that zolpidem is a type of drug. It's the same as Ambien, and its exertion is in the kidney. Okay, but now what do we do with those structured knowledge bases? So don't look at it yet. There are a lot of cool things to do. Almost every NLP healthcare solution uses them in some way or another. I want to focus on one non-trivial way, to inject this knowledge into word embeddings. So who here is familiar with word embeddings? Okay, so I'll do a very quick overview of what are word embeddings. When we're working with neural networks, we would like to be able to represent words as vectors. So we can input them into our neural networks, and we would like these vectors to have semantical meaning. We want the vector of zebra to be close to the vector of elephant. Okay, so these vectors are called word embeddings, and they need to have some semantic knowledge in them. How does it happen? How do we train them? So we take an algorithm, and we take a big corpus of not annotated text, and we train this algorithm to do some very, very specific, very, very basic tasks. Okay, עכשיו? Okay. We train the algorithm to do some very basic task on this text. For example, to predict the next word based on existing words, or to say whether two words appear together. Then we throw away this model. We don't really need this model. We throw it away. What we take is the weights that it learned to assign to different words, because these weights have learned something about the semantic roles of the words in the sentence. So this is how we train word embeddings, and the result is this. We have a vector representation that we can input into our neural network, and it will have implicit knowledge taken from the text. So this was general NLP. Now let's go back to healthcare and to how we use structured data sets in healthcare. So what if we could train those word embeddings not only to have implicit knowledge taken from the text, but also have the explicit knowledge that is in those data sets that we talked about? What if we can send it to medical school? So this is what was done in this very nice paper by Gabi Stanovsky. What they were trying to do is recognize mentions of adverse drug reaction, and they have this cool LSTM here. It's not really interesting. Let's look about what happens in the input level. So they actually use here two different sets of word embeddings. One set is pre-trained word embeddings on regular text, and another set that was trained on DBpedia, the graph, the knowledge graph that I showed you before. And how did they do it? So instead of feeding it with pairs of words and asking whether they appear together, they fed it with triplets of entity, relation, entity, and it had to predict whether this triplet appears in DBpedia or not. And the nice thing they did is that the loss is connected to the relation. It's in reference to a specific relation, so the two words that are close in a specific relation would be, the vectors will be close to each other in this projection and not in another projection. And they show how these word embeddings improve their ability to recognize ADR. But I'm reminding you that the main idea here is that they have two sets of word embedding. One is a medical student. He only knows what happens in this structured data set. And the other one is, let's say, a regular person that goes out and has fun and understands the word. Okay, and all the words that appear in DBpedia, they use the smart medical student embeddings, and all the other words, they use the regular embeddings. Another approach that is more holistic is from this paper from last year, where they actually trained one set of word embeddings that is both the medical student and the one that has knowledge about the word. And what they did is they trained a regular glove word embeddings, but they added to the loss a specific loss of the knowledge base. In this case, they used WordNet, that minimizes the distance between entities that are connected by a relation. So here we just have one holistic WordNet that knows both the implicit information from the text and the explicit information from our knowledge base. Okay, and now let's move to our last point, and I think it's the most important one that you'll hear here. So I'll show you two case studies Both are trying to save the same problem. And the problem is this. We have a free text radiology report. I told you before how it was produced. The radiologist looked at the image and wrote what it is. And what we want to have is this. We want to have a structured finding list that says that the person in this image was negative for pulmonary embolism, positive for pulmonary opacity, and so on. Okay, why do we need it? A lot of reasons. One of them might be that we want to train an image algorithm on these labels. Okay, so I'll show you 2 case studies who try to solve this problem. But first, I think we need to talk a little bit about the big elephant in this room, which is Hebrew. Okay, a lot of the data in the medical world in Israel is in Hebrew. And I just described some very cool stuff and approaches, but most of it is not available for Hebrew currently. What do people do in Hebrew? So there are actually a few very nice works, one of them by Raphael Cohen, who also presents here later. He did some really nice work on Hebrew, on expanding terms in knowledge base using transliteration. Of course, everything unsupervised, if you have enough data, will work on any language you want. And if it comes to this, you can always train your own parser, or you can take an existing parser and do some changes to it so it can adapt to your domain. For example, yesterday in the NLP workshop, Yuval Feinstein told us how they took an existing solution for parsing in Hebrew, YAP, and adapted it to the medical domain. So these all are stuff you can do, and they'll sound very cool. That's not what we did in Zebra. That's not what Jonathan Lazarson did. What Jonathan Lazarson did was very, very simple, but yet effective. He found 2 unique properties of radiology report that he could use. One of them is that radiology sentences are usually self-contained. Okay? They won't refer to each other. They would usually have all the information within the sentence. And the second one is that sentences reoccur and are shared between different reports. You can see an example here. These 2 sentences, אין לראות תסנינו גודש and צל הלב מורחב מעט בבסיסו, appear in 2 reports and in many more. So what Jonathan asked himself is, what if I did a lot of ugly standardization, okay? I clean the text, I take out all the punctuations, and I split the sentences correctly, and so on and so on. I standardize all the sentences. How many reports can I cover? So he actually found out that 20,000 sentences can fully cover 1.5 million radiology reports. So what he did was just tagging those 20,000 sentences with medical students, and it took about 2 months. And in the end, he had 1.5 million reports without any learning or understanding how medical Hebrew works. Okay, and what he actually did with those labels, like I said before, he used them to train an image algorithm. And I'm happy to say that about a month ago, a product that was based on this algorithm received an FDA approval. Much happiness. Okay, and now let's talk about another case study which uses another property of radiology reports. So Leo Tolstoy says at the beginning of Anna Karenina, happy families are all alike, and every unhappy family is unhappy its own way. And interestingly, this is also the case in the radiology world. The happy sentences, the no finding sentences, the no pneumothorax sentences are very common and look the same. And the unhappy sentences, the sentences when there is some finding present, would usually be unique because, like I showed you before, the radiologist would want to tell where it's happening and measure them and so on. You can see here an example of sentences and their frequency. Okay, so this case study, NegBio from Stanford, use this property. They start in a very simple and orthodox way, okay? They parse the text with bleep, which is one of the parsing solutions trained on medical text that I showed you before. They recognize mentions using a UMLS metamap. Again, it relates to what we talked about with the ontologies. But then they took a turn. Instead of labeling thousands of sentences and trying to learn or create rules that will match the hard positive patterns, they decided to recognize the negative, easy patterns using simple rules. And then everything that is not negative or uncertain is positive. And you can see here a couple of these rules. For example, here there's a rule that says that if your condition is modified with the word off by the word clear, then the sentence is negative. If your condition has a modifier of with evidence, which is in its turn has a modifier of negative with no, the sentence is negative. You can see here it's very simple negative sentences. Okay, and in this way they were able to label reports automatically with a very high precision and recall. So again, we can see here that if you understand the specifics of your data, if you understand the patterns, you can actually come up with places where medical text is easier than regular text. And you can use it to save yourself a lot of time and effort. Okay, so let's sum up what we talked about. I hope I convinced you that medical NLP is different from regular NLP and requires a special treatment. We talked about existing parsing solutions, and we explained that they can take you only part of the way. We talked about medical ontologists, and we showed how we can use them to have a smart neural network. And I also showed you how looking at the data and finding its specific properties can save you a lot of effort. I also recommend you to read these two blog posts that were very useful for me, and they have everything I say here and much more. And if it was interesting for you, Zebra NLP hiring an NLP researcher to work with me, so come to me after the lecture. Thank you.